Hi, this is Patrick and Mehdi from Zynga. Today we're going to discuss how we use deep reinforcement learning to personalize our games. So the agenda is to talk about what we mean by personalization and how this affects our user experiences. I'm going to step through a reinforcement learning application that we've applied at Zynga, and then Mehdi is going to discuss some of the challenges and the technologies we use for running reinforcement learning in production. So first, a little bit about Zynga. We're one of the world's largest mobile video game developers. We have over 60 million monthly active users and a wide range of really popular hit games. So feel free to check these out when you have some free time. Designing video games is a really difficult creative endeavor. With video games, you have complete control over the user experience, and there's so many choices to make. How hard should that level be? How high should the character jump? What bonus should we give after that level is completed? All of these choices can be difficult to make. Not only that, but our games aren't one size fits all. Different users have different skills, schedules, preferences. They're looking for different things in our games. What we'd like to do is personalize all of these little choices in our games in order to make sure everyone has as much fun as possible. So I'm going to formalize this notion of personalization a little bit. What I mean here, when we want to personalize some aspect of a game, is we want to look at the state of a user. So this could be history about them, what level they're at, their skill level. And then we want to select an action in the game, like how hard do we make the next level? And we want to make this choice in order to maximize a long-term reward. In the case of Zynga, we're typically maximizing engagement. So an example from our Willy Wonka Match 3 game is, how hard should the daily challenge be in order to increase the user's engagement? And we'll look at the user's current level, the history of challenges in the past, all types of information about their player performance. And one of the techniques we've used at Zynga really effectively has been rules-based segmentation. This is where our PMs will use rules to split the whole user base into different segments. Then each segment gets their own action. So this ends up looking like a decision tree you can see on the slide. If we're trying to decide how many gems should we give as a bonus, these different segments will split them based on how long it's been since they've installed. So if the user's installed for more than 7 days, they'll get 10 gems. Otherwise, they'll fall down a different branch of that decision tree. Our PMs will create these different segments and then use A/B testing versus a control to see what type of lift they get in our engagement metrics. We've had a lot of success with these segmentation techniques, but there's also some issues as well. First, it takes a lot of manual trial and error to develop these segments. It's not always intuitive how to split our user base and what types of actions, what type of personalized values are going to lead to an increase in our KPIs. So that's where the trial and error work, where it's simply exploring and running A/B tests to see what the effect on our KPIs are. But you're also limited in terms of the amount of personalization you can do. Since these are human-made, there's only so much data you're going to use in these different segmentation rules. Otherwise, it becomes way too complex. And the amount of values you can use for personalization is limited to the number of segments you have. So this wouldn't work if we were trying to, say, personalize the number of gems from 0 to 1,000. You're limited to a handful of different actions to choose from. And one of the other huge drawbacks is that it takes all this work to create the segments, but over time, your audience changes and becomes more mature, and our games change as well with new features. That means you have to repeat this work in order to keep your segments up to date and as effective as possible. Another methodology for personalization is with prediction models. So here, instead of using rules-based segments, we can train models that look at a wide range of user features, and for every available action, they can predict what the long-term reward will be for that user. After that, we can just pick the model with the best predicted reward and assign that action to each user. This overcomes some of the drawbacks because you can use a wider range of user features and there's some automation in this, but Using models does have its own drawbacks as well. You have to train lots of models, and that means collecting lots of data. And the data, the labeled data that you're using, is looking at the relationship of a user's state, the action assigned to them, and then the long-term reward, which means randomly assigning users to different types of actions and waiting for a long period that will act as a proxy for your reward. And this means you're giving your users less than optimal experiences along the way if some of these actions are clearly poor. You're also still limited to some simple outputs. It's hard to use these models to select the best action for each user from a continuous range. When we were looking at building our next generation of personalization technology, I came up with a wish list based on our history with these other techniques. We'd like to automatically tune the details of personalization. And this automation allows us to continuously explore and improve the algorithms over time, so we can keep up to date with changing audiences and changing game features. We'd also be able to personalize more complex actions. So we'd like to be able to personalize from a wide range of continuous values, or select say a multi-dimensional set of discrete actions. And we found that reinforcement learning seemed like the perfect paradigm. So reinforcement learning is a branch of machine learning, just like supervised and unsupervised. And with reinforcement learning, what you're doing is training an agent to interact with the environment. In our situation, that environment is typically basically users playing with our games. But the way the actions, or the way that an agent will work, is it has the state of the world as an input, and then it will select an action that maximizes a long-term reward. After the interaction with the environment, it will get a reward back, and that feedback loop is what allows the agent to learn an effective policy. The policy is the kind of encoding of how it makes a decision in order to relate the input state with an output action. And you've probably heard of a lot of the successes with reinforcement learning, with DeepMind training an agent to beat the world's very best Go players, to self-driving cars. So there's been a lot of breakthroughs in reinforcement learning, and we needed to see, will this actually work for our games? For that, we launched a trial application. So in our popular game, Words with Friends, every day we send out a daily notification. And this notification will remind our users that they have a move to make, one of their friends is waiting for them, maybe there's a daily challenge. And the tricky thing is figuring out what time of day do we send our message? Because we have a worldwide audience and everyone plays at their own schedule. Maybe you're working a night shift and you're playing at 3 a.m. The initial approach that the game took was to try to guess a user's time zone based on the country that they're in. And then it would send a message at the most popular time of the day to play. So there's already some issues in terms of guessing their time zone. And even if they have their own, what time zone a user's in, that may not fit their schedule since everyone can play at different times. But there's also a more fundamental issue with this. If we're predicting a user is likely to play at this time, if we send them a message, is that really going to be the best strategy for increasing our engagement? If we know you're going to play at 8 p.m., if we're going to predict that, would it actually be better to send a message an hour before or 12 hours before? Maybe that'll be more effective at increasing our engagement. And that kind of highlights the value of reinforcement learning, where it can look at that state of the user, a predicted time to play, and then it can experiment in an automated way with trying different policies and strategies, and it'll learn what works best. So when we launched our reinforcement learning application, we used the history of the user's hourly activity as their state. And we saw that the reinforcement learning agent was actually quite effective. We increased our click-through rate by 10% relative to what it was before. And it's now running in production for millions of users per day. So we can handle the scale of our wide user base as well. And this initial application kind of checked everything we needed for our test. It was scalable. It ran for millions of users per day. It was effective. We saw an increase in our click-through rate. And we could do this all with off-the-shelf technology. We didn't need to spin off our own research team to come up with algorithms. We could simply use open source libraries already available. With that success, reinforcement learning is now one of the core technologies we're using for personalization at Zynga. And now, Mehdi's going to talk about some of the challenges and the technologies that we use.
Hi, everyone. My name is Mehdi, and I am a machine learning engineer at Zynga. For the rest of the presentation, I'll be talking about the challenges we faced when training reinforcement learning agents, and I'll also present the technology we built in order to productionize it. The first challenge is in relation to the RL formulation. And by that, I'm referring to the process of designing the state and the actions for a given problem. The state is composed of a number of features. As the number of features increases, the state space increases as well. And RL is known to be sample inefficient, which means that a high amount of transition is required in order to learn an optimal policy. This makes feature selection challenging and very important. In our previous application, we purposely used small state spaces in the first few iterations. This allowed us to create a baseline, and then in following iterations, we could experiment with more complex state spaces to optimize the performance of the agent. The second challenge when it comes to the RL formulation is selecting the action space, which is challenging as well. As the number of action increases, the task becomes harder and harder for the agent to solve. When faced with a problem in which the number of actions is very high, we give the agent relative control instead of like a global control. So instead of having the agent select one of all possible actions, the agent can only select a change to apply given the previously selected action. The second challenge is in relation to training this training process. As Patrick mentioned earlier, the agent learns by interacting with the environment through a feedback loop. So that leads us to the cold start problem. How can we train and deploy an agent when we do not have any data collected already? For many of the problems we solved at Zynga, we already had historical data generated using other strategies like the segmentation-based optimization. We performed off-policy training so that we can start with a pre-trained agent instead of starting with a random policy. Hyperparameter tuning is also another challenging aspect in training the agents. Unlike in supervised learning, the training data does not have labels in reinforcement learning. So once we collect all the transitions that were generated by the agent, we train several new agents offline and use counterfactual evaluation to differentiate between the good and the bad one. In this final part of the presentation, I'll present to you the infrastructure that we built at Zynga to productionize these agents. RL Bakery is a deep reinforcement learning framework that we built at Zynga to standardize our training process. The framework wraps around TF Agent, which is a TensorFlow library, and provides a higher level API for training and deploying agents. RL Bakery is built to be generic and modular so that it can be applied to different use cases and different projects. We recently open sourced it, so if you feel like productionizing your own agent, feel free to clone it and use it. And this is what the training pipeline looks in our case. It's composed of several components which run sequentially in every cycle. Data ingestion collects the data required to train an agent, which are the observation, actions, and rewards. Data processing transforms the data to a format that is suitable for training and creates transitions. The model training component loads the agent that was trained in the previous iteration and trains it using the newly generated transitions. So once the newly trained agent is ready, we perform some analysis on it to make sure that it improved since like the training. Once that is done, we deploy the agent so that it's ready for real-time inference. We also have a monitoring component which runs after the deployment, and that component ensures that like the new model that was deployed and is live is working as expected. We use RL Bakery to orchestrate and run many of these components on Databricks clusters. Spark is also used to process and transform the data in a distributed manner. Finally, we use SageMaker to serve the model for real-time inference. Our last part of the presentation is about the Inference Service that we use to make real-time recommendations. Once a model has completed the training phase, it gets deployed to SageMaker so that it's accessible for real-time recommendations. We have built a service at the application layer that our game clients communicate with when they need to get a personalized value for a user or a recommendation. The application takes in the raw inputs or raw features and performs any transformation needed, such as normalization, standardization, or feature scaling. This service is also able to augment the user's features by loading some other pre-aggregated features, which can represent some summaries about the user's historical data, or some outputs of other machine learning models that run in by batch processes. Once the features are ready and that are in a format that is suitable to the model, SageMaker is called in order to perform the inference. In some cases, further post-processing is performed after receiving the recommendation from the agent. All data at any stage of the serving pipeline is logged to S3. This is required for both monitoring and future training iteration. So whenever the training pipeline runs, it loads the newly logged data from S3 and runs the training step in order to improve the agent. Once that is done, the agent is deployed again to SageMaker. So this diagram shows you the full cycle that our system goes through. In some cases, agents are scheduled to be trained daily, while in others, they are trained weekly. The training frequency depends on the amount of data we collect at each period and the maturity of the agent. We usually train agents daily when they first get deployed to production. In some cases, we decrease the training frequency to become weekly once they are stable, or when their policy do not change significantly every day. So as a conclusion, RL is a great candidate to use when personalizing user experience. It has the ability to optimize over the long term, which is not the case for other personalization methods, such as segmentation-based optimization. Using reinforcement learning agents in production comes with many challenges, such as challenges when formulating the problem and challenges when training and tuning the agent. Automating this process is also hard since it requires the collection of data from multiple data sources in a timely manner. There are several off-the-shelf frameworks that you can use in order to productionize RL, such as TF Agent and RL Bakery. Using these open source framework provides several benefits, such as lowering the development time, since you don't have to reinvent the wheel, and also getting the latest update and latest RL algorithms contributed by the community. We have applied reinforcement learning to personalize different aspects of our games, such as personalizing the push notification timing, and we did that with success. Now that we built a generic and scalable pipeline to perform both the training and serving, we will be applying it to solve even more challenging problems in the coming months. Special thank you to our team members, Kiran and Dashi, who contributed significantly to applying reinforcement learning at Zynga. Thank you.